Ductile materials, such as steel, usually exhibit the same strength when loaded in tension or compression. The strength criteria that are mostly widely accepted for these materials are the so-called Guest-Tresca criterion and the von Mises criterion. The criterion formulated by the French scientist Henri Tresca around 1864 and later reformulated by James Guest at the end of the 19th century uses the shear strength tau of n acting on any infinitesimal surface passing through a point in the body as critical index. N is the unit vector perpendicular to the surface. As n is arbitrary, the maximum shear stress tau max at any point of the body cannot exceed a given threshold tau 0, which corresponds to the allowable shear stress limit of the material. This is why Tresca theory of failure is also called maximum shear stress theory. Why this choice? Well, choosing the shear stress as critical index is motivated by the presence of defects in the lattice structure of metals called dislocations. When the planes of atoms are subjected to an excessive shear stress, they slip with respect to one another. Macroscopically, this is matched by the phenomenon of yielding. Thus, according to Tresca criterion, a stress is permissible if tau max is less than or equal to tau 0. Let us rewrite this condition in terms of principal stresses. Recall that the maximum shear stress corresponds to the radius of the largest Morse circle, which is half the difference of the maximum and the minimum principal stresses. Thus, Tresca criterion states that 1/2 of sigma max minus sigma min must be less than or equal to tau 0. How can we obtain tau 0 experimentally? So consider a simple uniaxial tension test on a bar and increase the load until the bar yields. The yield stress is close to the allowable uniaxial stress limit sigma 0. Let us draw the Morse circle corresponding to simple tension. As the stress increases, the diameter of the circle increases until it becomes equal to sigma 0. At the same time, the maximum shear stress attains the limit value tau 0, which is simply half sigma 0. Using sigma 0, Tresca criterion states that sigma max minus sigma min must be less than or equal to sigma 0. Since either one of the three principal stresses can be the minimum or the maximum principal stress, this condition corresponds to 6 inequalities. Sigma 1 minus sigma 2 must be between minus sigma 0 and plus sigma 0. Sigma 2 minus sigma 3 must be between minus sigma 0 and plus sigma 0. And similarly, sigma 3 minus sigma 1 must be between minus sigma 0 and plus sigma 0. These inequalities define an unlimited prism in the space of the principal stresses. Its axis is the so-called hydrostatic axis, that is sigma 1 equal to sigma 2 equal to sigma 3. And its cross-section is a regular hexagon. As the hydrostatic axis never intersects the boundary of the allowable stress domain, according to Tresca criterion, any hydrostatic stress is permissible, whatever its magnitude is. What is the physical explanation for this? Well, if a material element is subjected to equal principal stresses, there isn't any shear stress acting in the element, and yielding cannot occur. This is why, in principle, the material can withstand any hydrostatic stress. If the stress is plane, for instance, if sigma 3 is 0, the 6 inequalities that define Tresca criterion state that sigma 1 minus sigma 2 must be between minus sigma 0 and plus sigma 0, sigma 1 must be between minus sigma 0 and plus sigma 0, and finally sigma 2 must be between minus sigma 0 and plus sigma 0. These inequalities define an hexagonal domain in the plane of the non-zero principal stresses sigma 1 and sigma 2. Basically, this hexagon is the trace of the unlimited prism with the plane sigma 3 equal to 0. It is interesting to note that Tresca criterion captures the negative interaction that two principal stresses of opposite sign have in terms of strength. To better understand this, assume that a material element is subjected to a plane stress with equal tensile principal stresses sigma 1 equal to sigma 2. And let's simply denote by sigma the common value of the two principal stresses. As sigma increases, the stress point moves along the path labeled A in the plane sigma 1, sigma 2, and the maximum value that sigma can attain is sigma 0. Thus, under equibiaxial tension or compression, there is no reduction in terms of permissible stress with respect to uniaxial tension or compression. Conversely, assume now that the material element is subjected to two principal stresses of opposite sign, sigma 1 equal to minus sigma 2. And let's denote by sigma the modulus of the two principal stresses. As the stress increases, the stress point follows the path labeled B in the plane sigma 1, sigma 2. So the allowable absolute value of the principal stresses is only half the allowable stress in uniaxial tension or compression. Consider now a particular plane stress in which only one of the normal stresses sigma and one of the shear stresses tau are non-zero. This is the typical stress that occurs in beams, and we will call it beam-like stress accordingly. Let's see how Tresca criterion can be specialized in this case. Let's draw the three Morse circles that characterize this stress state. The radius of the largest Morse circle, which corresponds to tau max, is given by the square root of half sigma squared plus tau squared, and must not exceed tau 0, that is half sigma 0. We can rewrite this inequality as sigma gt less than or equal to sigma 0, where sigma gt is the square root of sigma squared plus 4 times tau squared and is called equivalent Tresca stress. Thus, the permissibility check when applied to beams obeying Tresca criterion is formally similar to the check for uniaxial stresses as long as the stress sigma is replaced by the equivalent stress sigma gt. Finally, if we square both terms in the inequality sigma gt less than or equal to sigma 0, we can rewrite Tresca condition for beams in the form sigma squared plus 4 times tau squared less than or equal to sigma 0 squared. In Morse plane, this inequality represents an ellipse centered on the origin. The stress at any point of the beam passes the permissibility check if the corresponding point of coordinates sigma tau falls within the ellipse. What are the materials obeying Tresca criterion? Well, this criterion is used as not only structural mechanics for metals, but also in geotechnics as strength criterion for cohesive soils such as clay in undrained conditions. In geotechnics, tau zero is called undrained cohesion and is usually denoted by symbols like Cu, Ku, and so on. Finally, note that Tresca criterion coincides with Mohr-Coulomb's criterion if the angle of friction phi is zero.